Now let's look at some ways to sample that help ensure getting a representative or random sample. So first one is systematic sampling, where we list the members of the population. We select a random number to start with. And then we select another random number, and we'll call that K. And then we choose every kth individual in the list, starting with the one that was randomly selected. So in the picture there, the first random number would be 2. We start with 2, and that's our first sample member. And then our second random number would be 3, and then we're going to choose every third population member from there. So we start with 2, and then we take population member 5, and then 8 and 11, every third member to get our sample. Okay, the next kind is stratified sampling, where we divide a population into subgroups or strata, and then randomly sample from each strata. Now, the key thing about strata is that they are chosen so that members of the strata all share a characteristic. So if I were to divide the class, the online statistics class into strata, I might choose to divide it in by year in college, okay, so that every strata shared the characteristic of which year in college. All right, so it kind of shows that in the figure as well, where the members of each strata share a color. Then we sample randomly from each of those strata, so all of the strata are represented in the sample. Cluster sampling starts off similarly, where we take the population, we're going to divide it into subgroups we call clusters, and then we use simple random sampling to select a set of clusters. So each of the clusters that are selected, all of the members are in those clusters are included in the sample. Okay, so you can see how in the example there are 6 clusters, 2 are selected, and all the members in each of those clusters are included in the sample. Now let's look at descriptive statistics. After we take a sample and we collect data, we're going to have lists of numbers, lists of words, and we need to summarize it to make sense of it. That's called creating descriptive statistics. There's 2 types. One is numeric. So we've already looked at mean and proportion. Those are numbers that are going to describe the sample. And then there's some other numeric descriptive statistics listed there, all of which we're going to look at this course. And then there's graphical descriptive statistics, things that are pictures that give us an idea of what the data looks like. Okay, so the first one, that would be a histogram. The second one is a scatter chart. And then that third one is a pie chart. And we can have graphical and numeric descriptive statistics that describe both qualitative and quantitative data. So let's look at some sampling and descriptive statistics for the population of the Math 240 online students. So again, the population is this class. We want to estimate that parameter of mean number of letters in the last name. We're assuming that we don't actually know what that is. So we take 5 random samples of size 6. So you can see those listed there. Sample 1 includes 6 values, and sample 2, 3, 4, 5, all of them include 6 values. Actually, I guess we have 6 samples, not just 5. Okay, so you can see different numbers show up in each of those samples. They're all different. And then we can calculate the descriptive statistic of sample mean. Okay, so if we look through those, we have 6.3, 7.2, 8.7, 5.7, 6.5, 6.7. They vary. They are not all the same. And none of them equal what we know to be the true population mean. Okay, they vary because of what we call a sampling error. It's natural variation that results from selecting a sample to represent an entire larger population. So the larger our sample size, the more reduction there is in sampling error. So that's something to keep in mind. Sample statistics usually do not equal the true population parameter that we're trying to estimate. Okay, so we can look at those sample means. None of them equal the 6.9 that we found for the population mean. Okay, but even though they don't equal that number, and remember, usually we don't know what number it is that we're trying to estimate, we can still use those sample means to estimate the population mean. Or if we're trying to estimate a proportion, we can use sample proportion to estimate population proportion. And then here is that, going back to that measure of certainty, our certainty is less than 100%, but we do have a measure of certainty in that estimate. Okay, so this might be the most important slide of this entire presentation, this idea that we are using a sample mean or a sample proportion to estimate some unknown population mean or population proportion, and we aren't 100% sure, but we will be 90% sure, 95% sure, 99% sure. We will have some measure of certainty. Okay, inferential statistics is then what we get when we take those descriptive statistics and add our measure of certainty to it, where we assess how certain or uncertain we are. That gives us inferential statistics. Okay, so we take that inferential statistics, and then that allows us to come to some conclusion about our population, make some kind of decision, make some sort of generalized a summary statement about the population that we are studying. Okay, examples of inferential statistics are confidence intervals, hypothesis testing, and linear regression. We're going to look at all of those this semester. So let's talk a little bit more about inferential statistics. So we're going to use this study as an example. Many Americans believe fake news is sowing confusion. Okay, that right there is an inferential statistic. It may not look like it, but it is a generalization about Americans. We're generalizing that many Americans believe fake news is sowing confusion. And then we've got a descriptive statistic there, that pie chart. It is a graphical representation of the data that was collected. Okay, so often statistics are presented in a way such that it's not obvious that it's a statistic, and it also implies that we're certain. Okay, so in that headline, it kind of makes it sound like, oh yeah, many Americans believe fake news is sowing confusion. There's no doubt about it. Well, we're going to dig a little deeper. We're going to find that there is some uncertainty underneath that. So it doesn't mean that they're bad statistics, but it does mean that we need to look for the statistics, the numbers underneath, the measure of certainty, and also sample size, because we know sample size is going to impact that variability, which then impacts our level of certainty. Okay, so here's what we can find if we dig a little bit deeper. So the following table shows the unweighted sample sizes and error attributed to sampling that would be expected at the 95% level of confidence for different groups in the survey. Okay, so we find that we have a sample size of 1,002, and then that plus or minus, that is giving us a range of values around those numbers that are included in the pie chart. That's actually a confidence interval, even though it doesn't look like it. All right, so what it's saying is if we take 64%, all right, where we get that 64% from that pie chart, that's the proportion of the sample that was taken that believe a great deal of confusion is being sown by fake news. If we take that 64%, we subtract that 3.6%, we get 60.4, and if we add, we get 67.6. Okay, well that gives us what we really mean by many. It really means that there's a 95% probability that the actual percentage or proportion of Americans that believe fake news is sowing confusion is in that interval from 60.4% to 67.6. Okay, so all we see in the report is many Americans. Okay, digging deeper, we get to the inferential statistics down below, which that many becomes the number and it becomes actually this range of numbers, 60.4 to 67.6, and the 95% is our measure of uncertainty, or our measure of certainty. Okay, so here is our